Hello everyone, my name is Kushal. I'm a PhD student at the Faculty of Aerospace Engineering at TU Delft. The title of my talk today is PIV based evaluation of coherent structures and skin friction drag reduction by spanwise wall oscillation. I have performed this work with my collaborators Professor Scarano, Dr. Elsinga, and Dr. Oudhouston at the TU Delft. So let's start the first broader question as to why skin friction reduction is important. Many industrial applications, like the shipping and the airline industry, spend a lot of fuel to overcome the drag forces which they experience. Up to 90% in ships and 55% in aeroplanes can be attributed to the turbulent skin friction drag that occurs at the interface of the object and the fluid. Due to the no-slip condition and the viscosity of the wall, a boundary layer develops, and owing to these large Reynolds numbers, this boundary layer is turbulent. And the aim of turbulent skin friction reduction is to reduce the slope of the boundary layer profile close to the wall, which gives a benefit in the fact that the turbulent skin friction drag reduces and the fuel consumption obviously is more efficient. There are many techniques that have been developed to achieve this turbulent skin friction reduction, but the technique of importance for this study is spanwise wall oscillation. Spanwise wall oscillation dates back to the early studies of Bradshaw and Ponticus, where a three-dimensionality was introduced into a two-dimensional flow using a curved surface. And it was seen that a reduction in wall normal motions was observed. Later studies by Driver and Hebbal, where a spinning disk was used, also reported similar results which supported the findings of Bradshaw and Ponticus. This led to the initial or the first studies on spanwise wall oscillation by Young et al. In 1992, where a DNS simulation was performed and these reductions in turbulent skin friction was confirmed. The first experimental study was performed by Ladhari et al. In 1994, where they used the setup on the right to perform hot wire anemometry measurements and also showed that reduction in Reynolds stresses and turbulent kinetic energy were quantified using the hot wire measurements. Later on, moving forward, in 2003, Quadrion Rico performed a DNS simulation at various parameters which govern these wall oscillations, of which the time period of oscillation, scaled by the inner wall variables, also represented as T plus, and the maximum wall velocity, represented as Wm plus, reported that up to 45% in skin friction reduction was observed at T plus of about 100. More recent DNS studies by Tauber and Lessinger in 2012 at a Reynolds number of about 500 showed that in the case that the wall is oscillated at a T plus of about 100, the streamwise velocity fluctuations lose their alternating spanwise streaky structure that can be seen in A. The main motivation for our study was that high resolution full field experimental data was not available, and to better understand the flow physics of what the spanwise oscillating wall does to the turbulent boundary layer. And with these aims in mind, an experimental setup was designed which consisted of a slider crank mechanism to balance the whole system. And the system was able to oscillate at an amplitude of 2 cm and frequency between 0 to 15 Hz. With these mechanical limitations, a free stream velocity had to be chosen to be able to achieve a T plus of about 100, for which a free stream velocity of 3 meters per second was chosen. The figure on the right shows a schematic of the acquisition locations and the experiment. To trip the boundary layer, Lego strips were used, which provided a thick turbulent boundary layer. Some of the descriptions of the PIV measurements are shown here. For the measurements, a recording device which was the SCMOS cameras were used, and low speed Nd:YAG lasers, also known as the evergreen lasers, were employed. While performing near wall high resolution PIV measurements, the first obstacle is that you also end up getting reflections at the wall. And these reflections, although a trouble, can help in accurate determination of the wall location. Here on the figure on the left, you can clearly see the raw velocity data indicated by the round dots. And due to the reflections of the wall, you also have a symmetric reflection of the velocity profile. By fitting a straight line close to the wall, and by observing the offset of the velocity at 0, the wall offset can be obtained. And by correcting for it, you obtain a corrected or a fitted turbulent boundary layer profile at the measured location. And also, to be able to obtain the resolutions required to resolve the near wall region, to be able to obtain the shear stress, anisotropic windows were used to enhance the near wall resolution. After which, the obtained velocity profile had to be compared with the corresponding DNS velocity profiles to assess for their agreement. And here on the left, you can see the plot of u plus versus y plus, and a clear agreement in the near wall region and the logarithmic region is seen for the planar PIV and the tomo PIV measurements. Similarly, Reynolds stresses also showed good agreement with the DNS data. The Reynolds number of the turbulent boundary layer was about 980 with a shape factor of about 1.36. So now that we have a turbulent boundary layer at Reynolds number of Re theta 130 and with the ability to measure the near wall region, it was important to quantify the drag reductions that were obtained. And the figure on the right shows the results that were obtained compared with the T plus and WM plus similar to that of Quadrio and Rico. And drag reductions of 15% were measured at a T plus of about 94. These reductions were also in agreement with the channel flow DNS data of Quadrio and Rico in 2004. The higher actuating frequencies and amplitudes were not obtained due to the mechanical limitations that have already been stated. And it is also important to note that the drag reductions are above the noise level and the uncertainty of the measurement. Moving on to the derived quantities to help understand the flow physics better, the Reynolds stresses at the optimum T plus of 94 show a drastic reduction, especially in the streamwise fluctuations. And similarly, when looking at the pre-multiplied turbulence production on the figure on the right, you can clearly see that the reduction is observed till the edge of the logarithmic region of about a y plus of about 200. Now that we've looked at some of the derived statistical quantities, PIV also enables the ability to visualize the whole flow field for the case of the planar 2C PIV measurements. So the figure here represents the instantaneous vorticity visualizations. The figure on the left shows that the wall shear layer represented in boxes 1 and 2 and the hairpin packets represented in box 3 and 4 dominate the vorticity fluctuations. When comparing these two, the vorticity visualizations of the stationary and the oscillating wall, it was observed that for the case of the stationary wall, these hairpin heads are always occurring in a train of hairpin vortices, also called as the packet of hairpins, as described by Adrian Manhattan-Tompkins. And it was observed that the wall oscillations have an effect on the packet number. That is, these hairpins which occur in trains are no more existing or as large trains in the case of the oscillating wall, where only 1 or 2 hairpins are seen. So the question now was, is there a connection between the oscillating wall and the number of hairpins in a packet? With this question in mind, we proposed a first principle turbulent drag reduction mechanism for the oscillating wall. If I bring your attention to the figure at the bottom, which represents the timing diagram of the wall oscillations, the wall oscillations can be divided basically into two regions. One where the wall has high wall velocity and the other in the green, which represents the low wall velocity. In literature, the works by Elsinga and Yodai, where they performed experiments in a turbulent boundary layer, reported that hairpins auto-generate at a time scale of about 30 wall scale units, and this corresponds to the low wall velocity region shown in green. So it was hypothesized that in the case of a stationary wall, hairpins are able to auto-generate and mutually induce a stronger ejection, which is essential in the wall normal transport in a turbulent boundary layer. But for the case of the oscillating wall, the rapid sideways motion of the wall prevents this multiplication or auto-generation of vortices, and therefore less intense and less frequent Q2 events are observed. Now with this hypothesis in mind, it was important to obtain 3D data, which was necessary to understand the mechanism further and develop the hypothesis mentioned. For which tomographic PIV measurements were performed with the help of Leon Bermel, who was a master student who was also involved in the project, where we performed tomo PIV measurements over the exact same setup with a volume of about 8 centimeter across 6.5 and with a vertical height of 8 millimeters. Phase average measurements were performed at the phases of the wall oscillation. And looking at the instantaneous vorticity visualizations, on the left you have the stationary wall, where green represents the isosurface of lambda 2 and purple represents the isosurface of wall normal velocity of about 0.3 meter per second. It can be clearly seen that in the case of the stationary wall, the vertical structures adhere to the low speed regions and form arc or cane shaped vortices. Whereas when comparing it with the oscillating wall on the right, it is seen that the oscillations disrupt the streamwise coherence and the entropy in the domain appears to reduce the case of the oscillating wall. To take this discussion forward, some preliminary quantitative analysis were performed where the mean entropy in the domain was calculated. And for the oscillating wall, there is a clear reduction in the case of mean entropy when compared with the stationary wall. So that brings me to the end of my presentation, and some of the main conclusions of it are that the near wall measurements of skin friction from PIV to quantify drag reductions over an oscillating wall have been performed, and a reduction of 15% in local skin friction is quantified experimentally at an RE theta of 1000. And a first principle hypothesis of the effect of wall oscillations on hairpin autogeneration has been proposed. Thank you for your attention, and you may now ask your questions.